Here's an example problem to take a look at. This is problem 14.92 from edition 10 of the textbook. We have a chain length L and a mass M falls through a small hole in a plate. Initially, when Y is very small, the chain is at rest. In each case shown on this slide and a later slide, we want to determine the acceleration of the first link as a function of Y, and then we want to find the velocity of the chain as its last link passes through the hole. In this first case, assume that the individual links are at rest until they fall through the hole, and in the later case, assume that at any instant all links have the same speed. And you'll see the reason why for that when you see the next picture. Ignore the effect of friction in both cases. So we're going to start off with defining a length, our mass per unit length. We're going to call mu the total mass of the chain divided by the length of the chain. All right. And then we're going to have a chain fall through the hole to a distance y right here. We're going to take y positive downward, and the mass of this length y is going to be given to us as m prime. And that's going to be mu times y, because mass per unit length times the length right here would of y would give us then the mass that's hanging out the hole. And this is the mass that has the velocity at any particular time. They all have the same speed. All right. Now we're going to let it displace downward a little bit at delta y right here, and we'll show you how to set up the equation to solve for this momentarily. So let's take a look at this again. We're going to apply the principle of momentum impulse. The direction is positive downward, as we mentioned earlier. And so if you start taking a look at this, you have mu times y right here for that initial length times the velocity it had at that instant. Then that's the momentum of the chain before this delta y took place, okay? Then you have the delta y, or excuse me, delta t of time at which the force of gravity is acting on this thing, and mu times y gives you the mass of the part right here, the y that's showing right there. It gives you that, and let's see if this pointer works. So it's this part right here, all right? And then times delta t gives you the external impulse. It's positive because remember downward is positive for our particular situation. This has got to be equal to the linear momentum afterwards, after the delta t of time. Well, what you have is a mass that's mu times y plus delta y. That gives me the total mass now of this part right here, okay? And then times a velocity, and the velocity is changed by v to a delta v, or a v plus delta v then for a final velocity. So if you start manipulating this equation around a little bit, we're going to do it by looking at these terms expanded out. Mu times y times v is going to be one term right there. Mu times y times delta v is going to be another term right there. Mu times delta y times v is going to be right there. And then mu times delta y delta v is right here. Now what we're going to do next is we're going to divide through by delta t. First of all, you notice this term and this term is going to go away, and every other term left has got a delta something in it. So we're going to divide through by delta t and then take the limit as delta t approaches 0. When you do that on the left-hand side, you're going to, there's those terms disappearing, as I said, and we'll form up the equation then. There was also, let me go back here right quick. The mu is now in every term, so it can be factored out as well. So there, we'll let it disappear away, and then we got these terms left right here. Now if we divide through by delta t, and we're going to get yg right here. Over here we're going to get y and dv dt, and over here we're going to get v and dy dt, and then with here the double delta is going to go away as you divide through by delta t into either one of these and let the delta t go 0. For instance, if you divide it into dy or delta y, you're going to get dy dt, but then delta v right here is going to go to 0 as delta t goes to 0. So this term is going to disappear for you. Now, can you see what we can do to simplify this? If you take a look at this, it's like we've got a chain rule here of y times g, and then if you take the derivative of yv dt, you'll get this term right here, okay? So right there is the result of taking d of yv dt. Now, from that point on, it's kind of a little bit tricky to try to get this set up so we can find out what the acceleration is and what we can find and the velocity is that we're after. So if you take a look at this, put the dt over to the other side, you get the equation looking like that right there. And then remember that v is equal to dy dt, so that means that we can rewrite dt as dy over v. We're going to put that in right there, okay? So what happens then is you get yg, and you're going to have dy over v equal to d of yv. Now, if you multiply through by a yv, you're going to end up with a yv over here on this side, and then a y dy right here. Let's see, is that going to come out right? We're going to get a y squared dy right there. Okay. So you get gy squared dy equal to yv d of yv. So this becomes easy to integrate over here. And remember, we started off with zero velocity and zero position, so the bottom lower limit is going to be 0 for us there. And then y squared is going to integrate out to be y cubed over 3. So you get gy cubed over 3. You integrate it from 0 to y, so that's why you only just get one term. And then you have this right here. So repeat that term again, and let's simplify it a little bit further. You can find that your velocity then is here, put the 2 over here with the 2/3, okay, and then you have a y squared, v squared right there. Well, the y squared is going to cancel out, leaving you just one y over here, so that's why there's 2/3 gy, and then you have v squared here, take square root of both sides. So it simplifies down to that for the velocity. If you want to know what the final velocity is, you plug in the final y position right there, which is the entire length of the string. And that's what we do. If y is equal to L, then you get 2/3 GL, and that is the velocity as you cleared the hole, okay? Now, of course, that's going to increase as time goes on, but you'll notice that if you did a free fall drop of this thing in the first place, you would ended up with square root 2 GL, okay? So anyway, let's take a look at finding the acceleration. The acceleration is equal to v dv dy. And so dv dy is going to be equal to, look at this right here, or this equation right here, I'm sorry. And when you take the derivative of this with respect to y over here on the right-hand side, you're going to end up with 1 over the square root of 2/3 gy. And then you're going to go inside and take the derivative of the argument there, and that's going to be 2/3 g. And so that's where the 2/3 comes from. Now, the 2 disappears because you got this all to the 1/2 power, so when you do the derivative, you're going to get a 1/2 that cancels out the 2 that's coming out of here, okay? So if you take a look at that, and you multiply the v, multiply this all by v, well, v is equal to that right there, so multiplying this together is going to cancel that out, and that's going to leave you with the acceleration equal to g over 3 then. And that's kind of, wow, that's pretty interesting. So what we're going to do next, and by the way, you notice that's a constant acceleration, so that's happening during the whole time period. So we're going to look at the chain, not in a pile falling through the hole, but actually falling through the hole. And as you're moving along, this chain has a velocity or speed, and that also has a speed right there. So, all right, so let it fall down just a little bit to a distance y. Just like we did before, we'll do another delta y of distance fallen. And then we start setting up our equations for this. You've got m, because all the mass is moving with velocity v. So the initial momentum of the system is mv, okay? And then you've got plus then the little increment of force right here of the external moment, or external impulse, I'm sorry. Mu times y gives me the mass that's through here, and g is the force of gravity on that mass through there. And force of gravity is not on all the chain, it's just on the mass that's falling through the hole. So that's why it's a mu y g and then delta t of time. And then we set that equal to the mass times the velocity, because all the mass is still moving, but the velocity is changed by delta v. So we have an mv plus delta v. Now, if you take a look at simplifying that equation, you'll notice that the mv right here and that mv are going to cancel out. And you're left with mu, which is m over L, times y times g times delta t, and that all is equal to m times delta v. So if you divide through by delta t and take the limit, delta t approaches 0, you're going to get, m's cancel out across here, by the way. So you're going to have y over L times G equal to dv dt. All right. And remember that dv dt is the acceleration, which can also be written as v dv dy. And I think you can see how we're going to separate out the variables here to work this one out. We're going to have the dy over here with the y and the g over L and integrate that out. And well, obviously, this is actually the acceleration already right here. If we back up and look at this term right here, this is the acceleration. So what we're going to have happening then, and looking at this, is that the acceleration is going to be equal to g over L times y. So it's just that term right there. Okay. Now, if we look at y over L g equal to v dv dy, if you're trying to find out what the velocity is, then we can separate out the variables and get, we'll have a y squared over 2, and then there's your g over L, and then you're going to have a v squared over 2. And so you can solve for your velocity out of this, and you get the velocity then as the, well, the 2's cancel out. Square root of y, y squared is going to be y, so you get the square root of g over L then times y. So for y equal to L, then your final velocity is going to be equal to the square root of g times L. So what we do is put L in here and then put it inside the radical, and it becomes L squared, and then L cancels out and leaves us with an L right there. So pretty interesting problem. The next thing we're going to look at is a 2,000 or 1,200 pound spacecraft designed to include a 2-stage rocket with stages A and B, each weighing 21,300 pounds, including the 20,000 pound of fuel. The fuel is consumed at a rate of 20 pounds per second and ejected with a relative velocity of 12,000 feet per second. Knowing that when stage A expels its last particle of fuel, its casing is released and jettisoned, and it wants us to determine the altitude at which stage A of the rocket is released, and B, the fuel of both stages after both stages have been consumed. So the givens to us are the total weight, which is weight of 12,000 pounds plus 2 stages here of 21,300 pounds each. So that gives us a total of 43,800 pounds, which is going to be m times g then. All right, the dWdt is going to be the rate that fuel is consumed, and we're told it's 5,000 pounds per second. So this is going to be it's like it's mg and a mass per unit time. So Q is going to be a mass per unit time right here. Okay. Now U, and this is where I differ from the textbook solution. They'll use this as a positive quantity. I'm going to use U as minus 12,000 feet per second, because I'm going to consider upward as positive, and we're told that the fuel is ejected at a rate of 12,000 feet per second. Well, if you're ejecting that fuel downward with respect to the rocket, that's a minus 12,000 feet per second, okay, because it's downward. So we're going to look at the velocity of the exhaust. We're going to call the velocity of the exhaust V sub E times J. Now, what is the velocity of the exhaust? Well, it's the velocity of the rocket plus the velocity of the exhaust with respect to the rocket. And so that's the velocity of the exhaust right there, V plus U. And then it's times J unit vector as well. Time to burn 1 tank of fuel is going to be 20,000 pounds divided by 5,000 pounds per second. So it's going to take 40 seconds then to burn a tank of fuel. So here's a picture of the rocket right now, and we're going to fire the rocket. Okay. Now we've gone up a position Y right here. We're going to look at it in general into its position, and then we're going to let it go a little delta Y of further motion, and that's our delta Y there. There is a corresponding delta V that takes place with this delta Y. Right? So we're going to apply the principle of impulse and momentum impulse. Direction is positive upward. So we start taking a look at the rocket when it's right here and talk about what is its momentum then. Well, its momentum is the total mass that it had minus the amount of fuel that it burned off, which is going to be Q times T, okay? And then times V right here. So Q is a rate at which fuel is burned, multiply it times the time, and you got how much mass has been burned away during the time period T that it took it to get from here to here, okay? So, and I'm talking about from the bottom right there up to where you are at this location. Now, if you go and look at this, we've got a external force acting on the system. That is your mass, which is the MQT right here, minus QT right here. That's your mass times the acceleration due to gravity times the delta T. The reason there's a minus sign here is because that force is downward, okay? And then that's equal to your new mass. Well, your new mass is, we burned fuel for a little time period, delta T. So the T right here has increased to be T plus delta T. To multiply it by the rate at which mass is burned off, you got the total mass then burned at this stage of the game. And then you got your mass is what you start off with right there in the M. So what you do then is you're going to multiply this times V plus delta V, all right? Because you had a change in velocity that took place. So as we expand this, I'm sorry, I left one other thing. We got the fuel that left the system, right? And that's a delta M times the velocity of the exhaust. And this is kind of a vector equation. And you might wonder, why shouldn't it be a minus sign? And the answer is it's going to be in that equation where we had that V plus U equals to the velocity of the exhaust. So it's taken care of. We expand this out to be minus MQT times V, and then we have a minus MQT times G times delta T. Now we're going to expand this term out here mostly. When you start expanding this thing, you're going to have a M minus QT times V. You're going to have a M minus QT times delta V. You're going to have a term that is minus QV delta T, so minus Q times delta T times V right there. You're going to have a minus Q times delta T times delta V right there. And then you're going to have plus delta M V sub B right there, okay? V sub B, though, remember we wrote earlier as the velocity of the rocket plus the relative velocity of the rocket with respect to the rocket, or relative velocity of the fuel with respect to the rocket, the exhaust fuel. Okay, when you look at this, you'll see that that's going to be a negative number, which is going to turn this all into a negative number as well, because the exhaust is being expelled a lot faster than the speed of the rocket is. So what we do is we start simplifying this out. You notice that and it slipped away there before I said anything about it. M minus QT times V and M minus QT times V is going to go away, all right? And so when we start expanding this some more, we have the M minus QT times G right here. In the process, notice that all these are delta terms, so we're going to be dividing through by delta T and taking the limit as delta T approaches 0. So that's why the delta T is missing right here. So we go to the first term over there, it's M minus QT times dV dt then. And then we're going to get a minus QV times delta T from right there. And then this is the double delta, which is going to go away, all right? And then we got a Q times V from right there and a Q times U from right there. And if you take a look at this, you can see that there's a couple terms right there that's going to disappear as well. So let's rewrite this then to be, this term is just repeated here, this term is repeated there. Those two terms are gone. We're now left with QU out there at the end. All right. Now the next thing we're going to do is we're going to separate out the variables here. And this is easier to do than that chain problem we worked earlier. So what happens here is that we're going to multiply across by dt, and we're going to divide by m minus qt. Let's take a look at that very carefully, because we got to get all the time terms together. So if you take a look at this, there's a couple of ways we could do this. If we divide through by this term all the way, we can get dv dt, and you'll have a g left, or minus g. So there's the minus g that's left right there. And then you have that times qu, okay? And we're dividing through by this right here, so we got a qu divided by m minus qt now, okay? So this goes away right there, that goes away, and then the qu is over m minus qt. Right there it is. We take it to the other side of the equation, it becomes a minus there because it was a plus on this side, and we're left with just dv dt, bring the dt over with us, and so we're actually integrating this problem right here. So the v, that's a repeat of what we just had there, and if you look at the v, integrate from 0 to v and 0 to t on time, you get that expression right there, and when you integrate that out, you'll get the u times the log of m minus qt minus the log of m minus gt, and technically that becomes u log of m minus qt over m, then minus gt, okay? So this is an equation showing you the velocity as a function of time. At t equal to 40 seconds, you plug your numbers in right there, and you'll find that the velocity that you have at the end of the first 40 seconds is 6031 feet per second. This is needed later. So, all right, now we have that right there. Again, going back, this was the velocity expression before we plugged in a time. We're going to integrate this again. And we're going to go 0 to y and 0 to t, and there's our log function right here, because what we're trying to do is find the distance now. So you're integrating all that out again, and when you do, you're going to get this expression right here for y sub a. So it's starting to get a little complicated, but you follow through your calculus and you can see what's happening. And then you're going to go, time is going to go 0 to 40 seconds. So what this allows us to do is calculate that y sub a is about 20 miles. Okay. Now, the next thing we're going to do is to get the height at the end of the second stage burnout. We're going to use that equation for velocity that we had from the previous. Now, what we're going to do is do another problem where we have initial velocity of v sub a. So when you do all that stuff we did before, you'll end up with a v sub a term that we didn't have before, because the initial velocity on the first stage burnout was 0. Okay. So you have that equation right there. You would again integrate from t equals 0 to 40 seconds and use this right here, because now W is 12,000 pounds and just one of the tanks. So it comes out to be this number right here. So it's a different M that we have now. Okay. And so when you integrate this thing out with the dy dt equal to all that, you end up with this expression right here. You're going to go 0 to 40 seconds. And then you're going to assume that you started out with an initial position of y sub a, because that's what you're looking at 40 seconds from the first burnout, okay? So when you plug the numbers into that, you get 126.8 miles, and that's the velocity, or excuse me, that's the position of the rocket as all the fuel is burned out. So what happens is, I get a little bit of fizzle there.